Okay, cool. So hopefully you can all see my screen now, can you?
Yes.
Perfect. Okay, so like I said, we're going to start very, very basic here. And obviously the most basic part of this is how do you get this program on your computer? So you often hear it referred to as ImageJ or Fiji, sometimes ImageJ. So the history behind this is ImageJ was originally created years ago as a project of NIH. And more recently, still quite a few years ago, this group got together and created Fiji. And Fiji is just ImageJ, but it comes with a bunch of biology-specific plugins already installed into it. So if you are downloading this for the first time, I definitely recommend that you download the Fiji version. And a lot of what we're going to go through today are plugins that come along with that Fiji version. And if you were just to download vanilla ImageJ, you wouldn't actually get these. So all I've done is Googled Fiji ImageJ. We go to the website, that's the wrong one. We want to go to this one, fiji.sc. And there's a download link here. All this does is it just downloads a zip folder, and all you do is unzip that folder and then throw it somewhere on your computer. So you can see I've just thrown it in my users D Richardson folder here, and it is this guy right here, Fiji. Okay. If you open this folder up and go into the Fiji app, then you have this ImageJ, because I'm on a Windows system, it says Windows 64. That is the file that I would click to launch the application. What I've done is I've created a shortcut somewhere on my desktop here, which is what I actually used to open the program. All right. The other thing that I'm going to point out that's really important here as well is this plugins folder. So although I said Fiji comes with a lot of plugins already installed, there's hundreds, probably thousands more of them out there that don't come with it. So if you ever do find one that can't be installed through the automatic installer, which I'll show you in a second, all you do is just download the file and drop it into this plugins folder. And these files are usually, it's usually a jar file. Or sometimes if it's someone's just done something in the ImageJ macro language, it'll be one of these IJM files, or sometimes it's a Java file. But once you have one of those files, you just dump it in here, restart ImageJ or Fiji, and then you'll have it available to you. Okay. Good. So when you do install Fiji, one of the things that it's going to do at first is it's going to run its auto updater. And the updater in Fiji is pretty neat. So if you just go to the help tab here, go to update. It's going to take a couple seconds. Yeah, my Java's out of date. And what it's going to do is it's going to search all of the different ImageJ update sites. And it's going to try and find any changes or updates that people have made to their plugins that you already have installed. And then it's going to also give you the option to go to these update sites or new update sites and new plugins that you don't have already. I'm just going to show you a couple of these once this chugs along here. There we go. So this, I obviously ran it this morning when I was practicing this, so there's nothing to update. If there was, it'd be listed here. But what I want to show you is this manage update sites down here. So if I click on this, these are all the different update sites that people have created. So you can just automatically have these plugins checked for. There's a couple that I want to point out. one that you should definitely have activated, and you do have to activate this separately yourself, it doesn't activate automatically, is bioformats. So bioformats is the interpreter that allows you to load in commercial files. So for example, the CZI files from all of our Zeiss microscopes. If you keep this bioformats up to date, it should be able to open all of those all of those files, even from our newer microscopes. There's always a little bit of a delay time between when Zeiss comes out with something new and it gets updated here. But as long as you have that box checked, it'll be as quick as you can. So you can see there's a ton of these. There's all kinds of them. I have no idea what half of them are, but there is great documentation. Either they'll have their own website for it, or on the Fiji wiki page, or there's an ImageJ wiki page as well, where you can find information on all of these plugins. All right. So you just put a checkbox in whichever one you want. You would close this, and then the apply changes would be illuminated here, and you'd click that, and it would automatically install those plugins for you or update them. And then again, you just restart ImageJ. The other thing that you're going to want to do when you first install this program is go to this edit menu and go down here to options and go to memory and threads. And so this is the maximum amount of memory that you're allowed to use. It's my son saying hi. This is the maximum amount of memory that ImageJ is allowed to use on your machine. So this is just my laptop, so I've got 8 gigs of memory. So I've limited it to using 7 gigs. This is also, you can tell it how many threads to use. So I have a 4-core processor here with 8 threads. It's multi-threaded, so we put in 8. And for any of the processing that's multi-threaded compatible, it will use all 8 of those threads. Okay. So there's some defaults that load in here. Usually this maximum memory is pretty low, so it's a good idea to come in and change this. It usually gets the threads right on its own. Okay. Cool. Okay, so what I want to do next is just load a couple of images here and just show you a few of the basic functions. So this little simple bar is all you get with ImageJ. And what I'm going to do here is I'm just going to go to one of the sample images. I'm going to get this mitosis sample. So this is a good image to play around with because it does a good job of showing us this, what ImageJ calls a hyperstack. So this is a multicolor image. So it's a 2-color image. There's a green channel, a red channel. What I'm going to do is I'm just going to change that red channel to magenta. All right, so we've got a 2-color channel. We have a Z stack, so there's 5 Z slices going through the cell. And then this is also a time-lapse image. Okay. So this is what ImageJ calls a hyperstack, when you have all of these different dimensions all put together, and they're all separated out by these different slider bars on the bottom. So the first thing that I want to do is I just want to pull apart one slice of this image.
Question.
Yes.
May I ask a question?
Yeah.
So I'm seeing both channels, yet I don't see all the Z stacks. What happens if I toggle the channels between one channel and the other one?
Yes. So right now, nothing happens. And that's a good question. So you probably can't see, but there's a little line around the outside here. And right now it's magenta. And when I go over here, it's green. So that means that if I choose to play around with, say, the brightness and contrast right now, it's only going to affect the green channel. But I cannot toggle those individual channels on and off. And it's because this is what ImageJ calls a composite image right now. And I will show you how you can actually do that. So what we're going to do is we're just going to pull out a single slice here. So I usually do this with a shortcut. Control-Shift-D is this duplicate function. And what I'm going to do is, instead of duplicating the entire hyperstack, I'm just going to do channels 1 through 2, z-slice number 3, and time point number 5. Okay, so that gives us this image. And I'm just going to move this one back so that we're looking at the same thing. Okay, so like I said, this is what ImageJ calls a composite image. So if we go up to the image tab here, color, and then we open the channels tool. Now with this tool, I can toggle these different channels on and off. Okay. If we went back to a color image, now this actually gives us the control on this color slider on the bottom, and it only allows us a single channel at a time. And this is kind of dependent on how ImageJ loads in the file. So it has to do with the metadata in the file, but sometimes you'll load in a file and it'll come in composite mode. Sometimes you'll load one in and it'll come in color mode. So just by having this little window box open, it allows you to easily switch between those or turn on and off the channels. Okay. Cool. So the next thing I want to do is, if we look at this image, I think you can probably tell this magenta here channel is really saturated. And so we're losing a lot of our detail there. So what we want to do is adjust our brightness and contrast on these two channels. So I'm going to minimize this one and get it out of the way for now. And what I'm going to do here is I'm going to go image, color, split channels. So that now I've got both of those images. To zoom in, zoom out, I'm just using the control key and either the plus or minus button. Okay. You can also use the little magnifying glass up at the top here. Okay, so we can, just by looking at this image, we can see it's a 16-bit image, and we can see it's obviously overexposed. So what I'm going to do is, there's this button up here that says Loop. This is your lookup table. And what we can do here is we can go to this HighLow Lookup table. And now this is just like the range indicator on our Zeiss microscope. So any pixel that's saturated is red, and anything that has a 0 count or is totally black is blue. And what I'm going to do is I'm going to go up here to the image, adjust brightness contrast. And that pops open this little window here. And now what I can do is I can see that the maximum pixel intensity here is actually a little over 6,000 counts, but right now the max is set down at 1,500. So what I'm going to do is just move this all the way out, and now you can see we've just got one red pixel right in the middle there, and we can see that one big structure is actually multiple structures. Okay, and we've got a couple 0 counts on the outside, so this looks good. I can either just leave it like that, or if I were to hit this apply button, it would redistribute the intensities on a 16-bit scale. So I'm not going to do that. It doesn't really matter because it's 16 bits. It'd be more important if you're looking at an 8-bit image. Okay, so then let's check this one over here as well. Oh, sorry, actually, let's put this back to magenta now again. And this guy will go into our high-low mode or range indicator mode. And we'll just adjust it so that we've got our one red pixel there now. And we'll just, the other thing I'm going to do with this one is this, all of this area out around here is just autofluorescence. So I'm going to try and get rid of most of that. Okay. All right, so now we can go back to green. Good. So that's starting to look a little bit better than what we had in the first place. Now, what I kind of want to do just for the rest of the time here is kind of show you a processing pipeline. So in my opinion, any type of image processing has 3 steps. First step is filtering, second step is segmenting, and the third step is analysis. And so the filtering that you do up front is just to clean up your image and make it a little bit easier to do your segmenting on. So what I'm going to do is I'm going to show you a couple filtering tricks on this image, and then we're going to do some segmenting and analysis on a different image. All right. So when you come in and bring us an image and you drop something off and say, oh, I really want this to look better, and we take a couple days and get back to you with something that looks better, you think we've been working on it for hours. The usual trick that we do is this. It's called a median filter. So what you'll find, confocal data especially, is always noisy. So what we're going to do here is go to the processing tab. I'm going to go down to the filters. I'm going to choose this median filter. And what this median filter does is it's going to look at every pixel in this image, and it's going to look around that pixel at a median of 2, what we have right now. And it's going to replace the pixel in the middle with the median value of all those pixels around. So this is a really good way to reduce noise. But unlike a mean filter, it doesn't smooth out your image as much, so it does a better job of maintaining edges. So if I just check the preview box here, we should see that image cleans up nicely. Okay, so this is pretty much the first thing we do all the time whenever anyone brings us data. And this radius, what you want to do is you want to match this radius to your data. So if you have really big structures, you would be doing this with a really big radius. You can see with this one, it just totally wipes it out. And if you have really small structures, then you do it with smaller radii. Okay, so that looks pretty good right there. Just going to hit OK. We're going to do the same thing to the other one. So processing, filters, median, preview, looks good. Okay. And so now I can put these two images back together again. So just go image, color, merge channels. It usually does a good job of figuring this out. So channel 1, except I don't want it to be red. I want it to be magenta.
Doc?
Yeah.
Hi, Doc. This is Putin. Can I ask a question?
Sure.
So speaking of the denoising or smoothing the images, so what is the difference between Gaussian blur and the median filter? So is there any difference between these two methods?
Yeah, so it's basically the opposite. The Gaussian blur is actually going to blur your image out more, whereas the median is giving you a little more sharper image.
I see.
There is one important distinction between Gaussian and median, is the median value is actually a measured value. It will not compute a different value. So if you have 5 pixels, it will take the middle value pixel, exactly the value of the middle value pixel, and replace that pixel by that value. It's not going to multiply your pixel values with a Gaussian curve. So it retains data.
Okay, thank you.
Okay. Sorry, this is dancing all over the place here. So what I want to do is just compare that back to this. So there's the original image that we started with, and here's what we've got to now, just with one pretty simple filtering step. Okay. Cool.
I think the it's not exactly matching it. I think it's on a different Z plane. No, or a different time. Yeah, well.
Anyway. Cool. Okay. So the next thing I want to go on to is just really quickly again, segmentation and counting. So what I'm going to do is I'm going to do this with a different image. So I'm going to go back here and I'm going to open the blobs one because this is very easy. But it's someone like segmenting and counting nuclei, which is something we do very often. So the one thing like can be a little bit tricky with ImageJ is, so when this opened up here, it says it's inverting the loop, inverting the lookup table. So that means when I go over here, so over this really black part of this blob, if you look up here on this toolbar, when I go over, it shows intensities. So it actually says that this is an 8-bit image, so the maximum intensity would be 255. And you can see that has a really high value, but it's black. So if you want to get this back to normal, you go back to the loop tab here, up at the very top, it has invert loop, okay? So now we're back to white objects on a black background. And before I actually get into segmenting, I'm going to show you one more filter that I commonly use that I really like, that I didn't show you on the last one. And that's down here under the processing tab, subtract background. And what this is a rolling ball background subtraction. So again, what you do is you insert a radius. And what it's going to do at each pixel, it's going to look around that pixel at that radius and try and calculate a background and do a background subtraction. So what this means is if you have uneven background or uneven illumination across your sample, you can do a little bit better job of removing that across your image. So the way this works best is what you usually do is just measure one of your objects first. So I'm just going to take the line tool up top here. And when I draw this line, you'll see on the information bar up here, you'll see a count of how many pixels long it is. And I'm just going to grab one of these nuclei, draw along it, and it looks like it's about 20 pixels long. Okay, so that's the value that I'm going to use for my rolling ball background subtractor radius here. We're just going to put in 20. Again, this allows us to preview it if we want. You can see that I did a pretty good job, except it made this awesome artifact up in the top corner here. Okay, so that's one of those things that you just have to watch out for. Whenever you're doing any of this filtering, you always have to make sure that you're not creating artifacts. Anyway, I'm going to leave it. We're going to live with it. And so now we've got this image, our background subtracted. And what we want to do is segment out all of these blobs. Okay. So the most simple way to do this is to just do a simple intensity threshold. So if I go up to the image tab here and I go to adjust, I can adjust the threshold. And so you can see I get this histogram here with my black pixels on the left, my white pixels on the right. And you can see right now that this is selecting for all of these black pixels, and because of that, the red is showing that we've selected all of our background. That's not what we want. We want the blobs or the pretend nuclei. So I'm just going to shift this one over and slide this one this way. And you can see this is actually a pretty easy image to segment. Okay. So if I hit apply here, what I'm going to get is what we call a binary image. So now all of those objects that I segmented out have a value of 255, as you can see up at the top there, up here. And our background has a value of 0. And once again, this loop is being inverted. Okay. And this is one of these times where you have to be careful with that. When you're working with a binary image here, there are a few specific processing functions that you can run on a binary image, and they want it to be this way. They want your objects black and the background white. So if we go up here on the processing tab, there's a bunch of binary options here. So if these edges were kind of noisy and we wanted to clean them up a bit, we can erode. So this should take away 1 pixel, unless I have this backwards. Yeah, perfect. So that's eroded those images and made them 1 pixel smaller all the way around. As you can guess, dilating would just do the opposite. Closing will be if you kind of have like little indentations and stuff in them, it should close those. And then if you have any holes in the middle of a structure, you can fill them with the fill holes option. Okay. Otherwise, I think this looks pretty good. Let's just dilate it back so that it's kind of close to what we had before. Okay, so that's how to do manual threshold of that image. Obviously, that's very susceptible to user bias. So there's a way to do this in a less biased manner. So if I just open up that image again, I'm not going to do the background subtraction on it this time. And what we will do is we go back into image, adjust. Now there's this option down here called auto threshold. So if I choose this, there's a whole bunch of different auto thresholding methods along here. And what we can do is we can just leave this as try all. And right now we actually have black objects on a white background. So I'll just turn this off. We'll hit OK. And it runs all these different algorithms. So you probably cannot see this on your screen, but it's run, I believe it's 16 different options. And underneath each one of these, it actually tells you which option it was. And so you can see that one there didn't do a very good job. It grabbed some things that we probably don't want. And so some of them have over-segmented, under-segmented, but we can look through here and find something that works pretty well. One of the most commonly used ones is this OTSU method. It usually works pretty well. It looks good. So what I'm going to do is I'm going to go back to this image, adjust, auto threshold, and I'm going to choose that OTSU method. Okay. Great. So now we've got our new binary image here where we've segmented out all those nuclei. So why don't we try doing some counting and doing some measurements on them. And the way we do that is we go over to this Analyze tab. And the first thing we want to do is go into the Set Measurements tool. So this basically tells us all of the different types of measurements that we can run. So I've got a few of them checked here already. We've got area, the mean pixel value, the minimum and maximum pixel value in each object, the perimeter, diameter. So you can check as many or as few as you want. And then we can go into our Analyze Particles tool here. And so what we do in here is we can give it an idea of what size of objects we're looking for. So right now this is just in pixels. So I'm going to say that it has to be at least 10 pixels in size. We can talk about how circular we want the image to be. So this basically measures its length and width and sees how similar those two measurements are to one another. I'm going to leave it just like this so that it gets everything right now. So it'll get the oval ones as well as the ones that are more rounded. And the other thing I'm going to do is I'm going to have it show these overlay masks. So that's going to allow it to show us exactly what it's found. We can tell it to exclude objects that are on the edges, so it wouldn't count these ones if we left that on, but I'm going to turn it off. and it's going to display our results for us. Okay, so we're going to hit OK, and that did not work at all. Cool. So I had to invert that loop. Let's go back. I'm just going to duplicate this time so I don't have to go back all the way next time. Invert that. I should remember everything I put in there. Ah. What am I doing wrong?
I think you need to invert the image, not just invert the lookup table. So edit invert will do it.
I duplicate this again so we don't have to go through that again if I don't. So this is another good point, the difference between inverting your loop versus inverting the actual values of the pixels. Oh yeah, right now. So see, these blobs are a 0 value, and the blackout here is our 255. So what we actually want to do is go back to the edit menu here, and under options, sorry, up above it's invert.
Yep.
Yeah. So we just choose this invert function. Now let's try this again. Perfect. Okay. So there we go. It counted 62 objects, and it's given us a readout of all of our data. But now, if you look, there's a big problem here. So it says our mean intensity of every one of these is 255. It also says that that's our minimum value and our maximum pixel value from each one. And that's not helpful at all, because what we actually care about are the values from our original image over here. So what we can do is go back to our set measurements window here. And there's something down at the bottom here that says redirect to. So what that means is we can take the segmentation from this image and look at each one of those ROIs in a different image that's also open. So what it's going to do is it's going to look at these regions, but take the pixel intensity data from this image over here. So under redirect, I just turn this back to the original blobs.gif. Hit OK. And then I'm just going to close this so that it doesn't get added to the bottom. And if we go analyze particles again, now our data actually has the correct minimum, maximums, and mean intensities based on this image back here. Does that make sense? Cool. So that's pretty much everything I wanted to show you today. The only thing I will say in addition to this is obviously this was all done in 2 dimensions. This can be done in 3 dimensions as well. On the Analyze tab here, there's this 3D objects counter. And it kind of works similar to the Analyze particles. So there's the 3D object counter options that you go into first and set up your options for it. And then you go in and run the 3D objects counter. This one, you don't have to threshold things ahead of time. You can actually do the thresholding right in there. And again, there's some really good help information for it on the wiki page. Cool. So that's all I had today. Like I said, it was just a really basic and simple introduction to ImageJ. If you have any questions, I'm more than happy to entertain those. Or also if you have just any other questions about image analysis outside of ImageJ, we can get to those too. But if anyone has any ImageJ questions, why don't you throw those out there now?
I'd just like to say thank you, Doug. I learned a lot.
In that very rapid and brief overview?
Yeah, you know, there's always this one checkbox or this one thing, you know, that I keep missing. Now just saw it again. It's great. Thanks. I think this was very useful.
Good. No problem.
Hi, I actually have a question.
Mm-hmm.
In order to do any co-localization analyses on 2D images, is it okay if we just subtract the background, convert it into 8 bits, and then threshold it, and then do a co-loc2 analyses, etc.? Or do we have to go 3D in order to have the most concise overlap? It's a great question, but in general, what would be your best approach?
Yeah, I mean, it depends a bit on your data and what you're wanting to get out of it. If it was a wide field measurement, I wouldn't see any reason to do it in 3D. I'd just pick a good 2D plane to it. If you're working in 3D, it gets a little bit different. And I'd say with co-localization, there's kind of 2 big methods towards it. So one is simply doing correlations. So it's saying, I look at my pixel values in channel 1, and I look at my pixel values in channel 2, and are there any areas where they correlate? So are there any areas of that image where they're high in both channel 1 and both channel 2? And that's kind of the way it's traditionally been done. But there's a lot of difficulties to that. Let's say you have one of your channels is expressed everywhere in the cell and the other channel is only expressed in a few small places. Depending on how you do that correlation, you can get totally different numbers. So the method that I prefer, and this also works much better in 3D, and it works when you're dealing with things that are blobs. So I guess the best example is if you're looking for co-localization in vesicles, so whether it's synaptic vesicles or endosomes or anything like that. You've got a bunch of blobs in both channels, and what you do is you pinpoint the centroid of all of those different blobs, and then you set some sort of threshold and say, okay, if I have a centroid in my magenta channel and a centroid in my green channel, and those are within 3-4 pixels of each other, I'm going to call it co-localized. And in my experience and what I've seen, that's like the best and most optimal way to do it, and seems to give you the most robust and reliable data from it. The correlation stuff is much more difficult to use. You do have to be very careful about how much background you're subtracting. When you acquired the data, was one channel blazingly bright and the other one was really low counts? You have to be much more careful on the acquisition side of it as well. Whereas finding the centroids and just measuring distances is a little easier on the acquisition side, but obviously more challenging on the analysis side.
Thanks. Just a very quick follow-up question. So how do you feel about the costs correlation then? Do you think it's an outdated method, or does it reflect pretty good in terms of any co-localized patterns that are in similar brightness? Thanks.
No problem. Aaron, Chris, feel free to chime in too if you want to say something. I just say that as far as the correlations go, it's very important to do something like the Manders coefficients do, where it does take into consideration how much of each marker is there. So like when I said, when you have that situation where you have green everywhere and magenta only in small areas, you don't want to calculate how much green co-localizes with magenta. You want to calculate how much magenta co-localizes with green.
I think an important distinction also is the co-localization on the level of, let's say, entire tissues or entire big pieces of muscular fibers or whatever is a different thing than co-localization of vesicles inside of a nucleus. I think the classic co-localization comes from that macroscopic kind of view where you're trying to compare expression levels of, let's say, a green species and the red species, and they're in the same place, but their intensities go together. And that is the Manders coefficient, is saying if something is bright in the red, it will also be bright in the green. And if you look at another cell, it will be slightly dimmer in red and it will be also dimmer in green. And you can accompany that, and that is what gives you the diagonal in the correlogram. This is different than a case where you would have, yeah, they do co-localize. I have green on top of red, but sometimes the green is brighter than the red, and sometimes the red is brighter than the green. And even though they are on top of each other, they do not correlate, right? And those are two different important flavors of the co-localization. And Costis algorithm, just to go back to the question, works on this macroscopic kind of thing. Is where you're looking at the correlations rather than the coincidences.
Thank you so much.
Cool. So I saw Lynn had a question in the chat here. Can I count leukemic colonies using this counting analysis method? And if yes, is a special microscope required for this? So what I showed you there today could definitely be used for that. It's the only thing that's important is that you have good contrast between your colonies that you want to count and the background. Other than that, you can do it in 2D, you can do it in 3D. You can do it with a wide field scope, a confocal scope. It doesn't matter. But yeah, as long as your colonies have really nice contrast to the areas around them, you don't have a lot of holes or a lot of intensity variations within the colonies, it should be pretty simple to do with what I just showed you there today.
I guess perhaps another important aspect on top of that, Doug, is that suppose you'd have leukemic cells versus non-leukemic cells side by side. So maybe you'd have to find something in the leukemic cells. Maybe they are rounder, maybe they are dimmer, maybe they are elongated, maybe they are flatter, maybe they, I don't know, maybe they have structural parameters that distinguish them from the other cells. Even if they have, let's say, similar intensities, maybe they have other types of contrast, not just intensity.
Yeah, and when you run into that, you might need something a little more advanced than what I showed today.
Well, you had the filters in there where you had circularity, for example, right?
Yep. Yep. No, for sure. Excellent. Any other questions? Good. Hey, if anyone's got some like non-Fiji questions, or they just had a specific question about something they've been working on the last few days and wanted our help with it, I'm going to turn off the recording right now.